How's everybody doing? Professor Bryant back, another installment of Workout Wednesday. Today, our focus is going to be on, again, we're sticking with equilibrium still, but we are focusing on interpreting a graph and being able to graph what is expected to happen in a particular equilibrium situation. So we are still working with the equilibrium workbook from the supplemental worksheets, and we're looking at, this is on the last page, or the second to last page of the workbook, and this is question number 4, which talks about the Haber process. And we spoke a little bit about the Haber process, which is considered fixation of nitrogen. So we take nitrogen gas with hydrogen gas, and we create ammonia, and that is an equilibrium reaction that is exothermic, right? So we create energy. And they tell us that we have a 1 liter container filled with 7 moles of ammonia, and the system proceeds to equilibrium as indicated by the graph. So we have NH3 as our only component. So even though we have a particular reaction, and I've redone this here on the sheet I printed it out, even though we have a multi-component reaction, we have started with a product. So this is effectively turned around, but we can still work with it in its current format, and I'm going to show you how to do that and how to understand what is happening. They've also given us a graph, and we'll come back to the graph for now because they've already given us how ammonia decreases over time. But we need to determine the amount of the 2 reactants that will be formed once equilibrium is reached. And to do that, you can utilize an ice table. So what I have drawn here and filled in here is an ice table. We now are dealing with a scenario where we have zeros for the reactants. Now, I haven't seen many of these examples thus far, but it's the exact same concept. Whether you start with products or reactants, if it is initial, we are just starting a reaction, whether it's a reverse or forward reaction, we should understand that there will be no reactants in this particular reaction because we have not been told that there are any. So we assume that there is 0. Now, generally speaking, we have had minus X's underneath our reactants, but in this particular case, we have plus X. Why? Because the reaction is moving in the reverse direction, or the reaction will proceed to the left to achieve equilibrium. Hopefully we understand that it will move to the left to achieve equilibrium. So because of that, because we have been told by the graph the amount of ammonium at equilibrium, we can then deduce the amount of H2 and N2 that will be created, and from there we can calculate K. So what I've done here is I've put 7 with 2 zeros, plus 3x, which is a function of the stoichiometric coefficient, plus x, which is a function of the stoichiometric coefficient, and minus 2x, which is a function of this stoichiometric coefficient. And what you will see is that instead of utilizing an x here, what I have done is put in the value that was determined by graphical analysis, right? So this is the connection that you have to make, being able to utilize and apply information to a scenario. This one here comes from the graph. This is not pulled out of thin air. It's not told to you in the problem, but you have information. How do we know this is the equilibrium concentration? Because we see no change in concentration after this point in our reaction. Therefore, the system will be at equilibrium. So if we put an x and a 3x here, then we can deduce from the math of 7 minus 2x equal to 1 that x is equal to 3. And you can do that quick algebra on paper if you like, or in your head, but realize that 7 minus 6 equals 1, so 2x must equal 6, so x equals 3. So the amount of N2 at equilibrium is equal to x, so therefore N2 should have a molarity of 3, and H2 is equal to 3x, so H2 should have an equilibrium molarity of 9. So I just utilized a tool, the ICE table, and graphical data along with the question to solve this. This may not be the way a question is formatted, and you may not have seen questions formatted like this, but you need to be able to have the understanding to apply that to solve for this, because that's pretty straightforward. Okay, now they've asked us to calculate Keq. Knowing this information, Keq expression is pretty straightforward, right? Products raised to the stoichiometric coefficient divided by the product of the reactants raised to their stoichiometric coefficients, and we see that Keq for the forward reaction, right? The forward reaction, which is the above, is 4.5 times 10 to the negative 4. Notice that it is reactants favored. It makes sense if you look at the concentrations of the two reactants are higher than the concentration of the products. But I have written this Keq as product over reactant, and that's why we have this value. So for the above reaction, we should have more reactants than products, and we see that. Now what I've done here is show you that the reverse reaction, if we were to write this in the opposite direction, then it would be products favored. So if we were to reverse this, you could have still done this problem if you were to rewrite the equation. Realize because Keq for the forward and reverse are inversely related. So now, asking you to draw and label the graph, what you see here is that at the point of equilibrium, which is here, what I've listed with this line, you should expect no change in concentration for any of the components. And we know the equilibrium concentration of both components, 3 and 9. So we need to find 9 on our graph. We need to find 3 on our graph. And then we realize that since we are starting from 0 for each of these, we're going to have a rise of concentration over time, and then it will flatten for both of these. So this is a great question. I love a question like this because it asks, it incorporates graphing, it incorporates the components, the content, the mathematics, and a little bit of intuition, understanding about equilibrium. Again, if you have any more questions, feel free to reach out via email or leave a comment.